Okay, in this lecture, we'll continue to discuss volumes of a solid of a revolution. We're going to learn a new method called cylindrical shell method, which is based again on Riemann sum. Let's check out a region enclosed by some graph. Suppose this region is rotating around the y-axis. We would see a solid in the shape of, say, a donut. Now, just like how we apply the washer method, the disk method, to come up with definite integral for volume of those solids, this time we'll instead pick up a strip first, not the whole region to start out. Let's try a strip. If we revolve a strip only first, the revolution of the strip is in the shape of a shell, cylindrical shell. That's why this method is called cylindrical shell method. Now, of course, to go through the process of setting up a Riemann sum, we would slice the region and get in many strips, revolve each other strip. Right now we'll just see what we can do with the revolution of one strip. So we got the cylindrical shell. Now, idea is if we can figure out the volume for one shell, then volumes of all those shells added up would give us a Riemann sum. Then we add them up, then we have a definite integral. Okay, so again, the key is to figure out volume of one shell. Now, to derive formula for volume of one shell, let's take this shell out of the picture. Just focus on the shell and see what kind of formula we can come up with. Okay, this shell is taken from here. So the height, suppose the height of the shell in here is h, so this is h. Notice the cross section of the shell is a circle, so there's a radius that be same as the radius here, called r. Alright, the strip we pick it up is a vertical strip at the location x with thickness dx. So the thickness of this shell is dx here. Now, how are we going to find the expression for volume of this shell? Let's do this. Imagine a cut along the side of the shell. Then open up Alright, so let's continue to open this up and flatten it. Approximately, we obtained a thin wall. Now, this thin wall has two sides. The side facing us technically is shorter than the side in the back. The side facing us is here, so we like the inner wall of the tube or cylinder. So you can imagine this side is shorter than the back side. Okay, since dx is very small, we always take dx small. Basically, the length of dx will approach 0 when we do the limit in the Riemann sum. So anyway, it's very small. Since dx is very small, in order to come up with a formula for the volume of this wall or volume of this shell, we regard both sides to be the same, identical. Therefore, this wall is approximately a thin box. Now it's considered as a box, and we have a formula for box: length, width, height. Length is, say, L for now. Width is dx. The height, well, the height be the same here, h. Right? Now the height can be determined from the graph up here. What about the length? Well, if you trace back, the length here is the same as the length here, and that's also the same as the circumference. So that's 2 pi r. We know how to do that, as long as we know how to figure out the radius. Alright, so our dv equals the product of those three. Now let's copy down the length. Let me write down the height first. Product in his switch. Height dx. Alright, so this is the formula for volume of a shell. In this formula, there's dx. In other situations, we will have dy if a horizontal strip is picked up to generate a cylindrical shell. So it depends on how the region is revolved. Alright. Now, the radius here, as we see here, the height of the shell, a distance here, we actually consider this a vertical distance or horizontal distance. Okay, they are both the functions of x, the location where we pick up the strip. Different location, the height will be different, the height of the strip will be different, the radius will be different. For this reason, r is a function of x, h is a function of x. If we go through the Riemann sum process, so we would add them up: 2 pi r x I, like the ith strip, h x of I, delta x, I from 1 to n, then n go to infinity. That's basically to add all this up and we come up with our definite integral. A to b, say this spot is A, this spot is B. Our strip would start from left end at A, moving cross region, stop at B. That's why A to B dv, or integral A to B, and this is our dv. So 2 pi r h dx. Alright, so this is our method of cylindrical shell. Now this method, two things we need to be careful about. That's one, the location we pick up a strip, vertical at x. If it's a horizontal, we need to clearly mark it at y on y-axis. Another thing is the radius. We see the radius in the graph is this. It's correct. But when we do problem, it's important, it's better we mark the radius in the middle to avoid confusion, as we're explained in concrete example later in this video. Alright, one more thing we notice is the graph gets a little bit more complicated. We got vertical distance, horizontal distance. If possible, it's better use different color to mark different things involved. All right. Okay, let's get to example. First, let's see this problem. Find the volume of the solid generated by rotating around the y-axis, the region bounded by graphs of y equal to 25 minus x squared and y equal to 0. Okay. The graph of y equal to 25 minus x squared is problem. It's important to draw the graph, see the region, do the revolution. Otherwise, it's impossible to come up with anything right. Okay, so this is graph of y equal to 25 minus x squared, and this is y equal to 0, which is x-axis. All right, now it's clear the region enclosed by those graphs is this. Okay, so this region is rotated around the y-axis. It's going to generate a solid like this. The graph of a solid is not required. I'm drawing it here because this problem is a little unique. I want to explain something. So you can see if this region is rotating around the y-axis, this will be the solid that's going to be generated, right? Now, one thing I want to point out is, in order to generate this solid, yes, we rotate the region, shaded here, but as we notice here, half of the region would generate the same solid if rotated around the y-axis. This is true because the region is symmetric with respect to y-axis around which region is rotated, right? So it's important to notice that only half of the region is actually required. If we use the whole thing to do it, to set up the integral, then we would get the wrong answer. We would get a double answer. So we would come up with two basically identical solids. That would give us a double the volume. That would not be right. Okay, we'll talk about it later when we determine the limits to use A to B. All right. Okay, so we decided to use only half of the region to do it. Let's pick up a strip, rotate around y-axis. What do we see? Cylindrical shell. So the method is 2 pi r h. Now it's a vertical strip, so it's a dx at location x. Clearly indicate the location. Very important. We need the fact that the strip is picked up at x. All right. Now, there's a dx, of course. Now let's determine expression for r to plug in, expression for h to plug in. So we come up with explicit expression for volume of one shell. Start with the radius. Now, radius from the graph, well, we see is this. Like mentioned earlier, when you mark the radius, mark in the middle, not at the top, not at the bottom. All right. I'll explain to you at the end what would happen if you mark it at the top, for example. All right. What problem you could run into. So radius is here. Now, first thing we notice is this radius is a horizontal distance. So horizontal distance, like before, write it down, horizontal distance, and that's x right end minus x left end. Okay, so this will tell us exactly what kind of expression we're looking for. We're looking for x value or x expression, x equal to. Alright, so now go back to the picture, of course. That's why I said you gotta have the picture. This is the x at the right end. What's the x value or expression at this end? It's x. And this is why it's important to clearly indicate the location x. So x at this end is just x. Now x at the left end is 0 in this case because it's on y-axis. So we find the expression for r. Now plug in. Next, we determine h. H is the height of the cylinder. Is a vertical distance, the type of distance, so we know the formula. YA, YB, Y value or Y expression above. And we see clearly it's here. This is the Y value at the top end of the strip. This point is on the graph of y equal to 25 minus x squared. Alright, so we also identify the correct equation, y equal to 25 minus x squared. Now we need to make sure it's in the right form. Now how do we know it's in the right form? Well, this is y equal to value, y equal to expression. This is y equal to expression, so this happens to be in the right form. We can plug in directly, otherwise we would have to solve the rewrite. Okay, YB, well, we can see clearly y value at the bottom of the YB is 0 because it's on x-axis. Alright, so we plug in, it's actually just 25 minus x squared. Just drop to 0. Now this is the volume of one shell. And then our strip, red strip, will start from this location at 0, moving across the region to stop at this spot, which is x-intercept of this parabola. We can figure out very easily. Set the function to 0 and solve, we get the plus or minus 5. So this is a positive 5, this is a negative 5. But from the picture we see we're going to go from 0 to 5. Alright, so that's the correct range for variable x or strip. So write it down, it's going to be 0 to 5. 2 pi, now multiply x through, so it's 25x, x to the third power dx. Alright, so here, whether you pick up the whole region or half of region matters. If half region is picked up, you go from 0 to 5, which is the right way to do it. If you are not paying attention to the symmetry of the region, the way it's rotated, you start from negative 5 to 5, you would double the volume, which is not right. Okay, this doesn't happen all the time, but it happens, well, like here. So you got to pay attention to that. Okay, the rest is just to find the antiderivative and then calculate. 2 pi copy down. Antiderivative of 25 is 25x squared over 2. Antiderivative of that is x to the fourth power over 4. So there's a 5 plug in, there's a 0 plug in. So 25 times 2 pi times 5 plug-in is 25 times 25 is 625. 5 plug-in for x, it's again 25 times 25. It's 625 over 4. Then you plug in 0 for x, you end up with a 0, 0, so it's just 0. So the final answer is 2 pi times, this is half of that, so we just have 4. Final answer, 625 over 2 pi. 2 cancel out the 4 left. So this is the final answer. This is the volume of this solid. Alright, before we move to a new example, I want to comment on again the location where we mark the radius as I indicated in the middle, not at the top, not at the bottom of the shell. What could happen if, say, you mark it up here? Graphically, looks like the same. Indeed, they are the same distance, right? Same radius, nothing wrong. But when you try to determine expression for the radius, say you would rely on this formula. Whether it's down here or up here, it's horizontal, so you're going to do this. The problem is, in this case, if you try to determine x at the right end, then you are looking at the point here. So the problem is the point happens to be on the parabola. Many times students get confused, misled, and they just think, oh, probably the expression would have something to do with equation of the parabola, right? Wouldn't that be wrong? The correct value or location of x r is x. So if you mark your radius up here, sometimes it's not easy to know which one is right, which one is not right. But if you draw the radius in the middle, then this would have nothing to do with the parabola. It would be just a location of the strip, which is x. So it's important you not only clearly indicate the location of the strip x, also draw the radius in the middle to avoid any confusion, making any mistake. Alright, so this is the method of cylindrical shell. Let's see another example. Find the volume of the solid generated by rotating it around a line y equal to 5, the region bounded by its graphs of y equal to x squared and y equal to 2x. Okay, so let's put x-axis down here because I know there's a y equal to 5 involved. I purposely want to have more room up here. You'll see. Okay, this is x-axis, this is y-axis. There is a y equal to x squared. That's parabola. Most of the functions involved are simple. Parabola, straight line like this. So we can pretty much just graph by hand. Y equal to 2x. Now it's clear. The region enclosed by the graphs of y equal to 2x straight line and y equal to x squared, which is parabola, is this. Shaded a little bit. This way, make it easier to determine range of the strip later on. Alright. Now this region is revolved around y equal to 5, so y equal to 5 is somewhere up here. Okay, a lot of things involved. Try to use a different color to make it easier to tell what's what. Alright, now let's pick up a strip. Well, we're gonna pick up a horizontal strip. Horizontal strip, if extended in this case, would intersect with the y-axis. So at the location y with the thickness dy. Alright. Now let's revolve. So we actually see the revolution as a cylinder. Revolve this end around y equal to 5. Revolve this end around y equal to 5. Look, both ends are as far from the line, so they would generate as big a circle. Then we start to see pretty much a cylindrical shell, right? So its cylindrical shell, the formula is dv equal to 2 pi rh dy, which we already determined. Okay. Well, the rest is pretty much like always. We're going to determine expression for r, expression for h, plug in, and then set up definite integral. Now, h is obvious. That's the length of the strip. R, radius. Remember what I said? Don't mark the radius at the front end or back end of a cylinder. Rather, mark it in the middle. Okay. Now let's try to determine R first. R, from the picture we see vertical distance. So it's a vertical distance is a YA, YB. Now what's the Y value above? It's 5. We can see from the picture. You have to have a picture. What's the Y location or Y expression at the bottom? It's at Y. That's it. So plug in 5 minus Y. Next we determine H. H from the picture we see it's a horizontal distance. Horizontal distance is x right end minus x left end. Okay, look at the picture here. The right end of the strip is on the graph of a parabola, which is represented by y equal to x squared. Okay, so this is the right equation, but it's not in the right form. Why is that? Because we're looking for x equal to. It has to be x equal to something. X equal to number, x equal to expression to plug in, right? So the equation is not in the right form. We need to solve for x. And that's actually simple once we know what we're looking for. We solve y equal to x squared for x and rewrite it as x equal to square root of y. So that's what we need to plug in. Of course, algebraically, if you solve this, you get plus or minus, but this end, this half of the parabola where we find the point is positive, so we use only the positive square root of y. The negative is never used in our problem. Okay. But anyway, so you can see the importance of using this little simple formula. So you know the right form to plug in, not just the right equation involved. Okay, x at the left side. Well, again, x left side, the point is on the straight line. So this side basically is represented by y equal to 2x, but again we need to solve it, so we have x equal to plug in. So this is pretty simple, just divide by 2. So x equal to y over 2, plug in y over 2, right? And notice we pick up horizontal strip and we determined that earlier on, you know, the y is the variable, dy everything, so everything must be in y. Seems like, you know, we are on the right track. Here we plug in, so it's a square root of y minus y over 2 dy. All right. Now simplify before we add them up, before we set up a definite integral. So 5 times radical is a power, so 5 y to half power. 5 times that is a 5 over 2 first power. Negative y half power of y is negative y to 3 half power. Negative is positive, so it's positive half y squared. Basically all powers of y. So this is expression for volume of one shell. Now our region basically is sliced into many strips like that. That's just a representative. Every one will generate a washer like that. Not washer, I'm sorry, shell, cylindrical shell. So we're going to add this kind of volumes starting from the bottom. So the very first one is at y equal to 0. Now with the region clearly shaded, we can see the red strip will move from bottom to top, stop at somewhere here. So we start from 0 to whatever number here. Now how do we find the number there? Geometrically, it's the y coordinate of the intersection of those two graphs, parabola, straight line. So algebraically we just set them equal to each other and solve. X squared minus 2x equal to 0. Factor the x equal to 0, x equal to 2. But the way we solve it, we find actually the x coordinate of intersection here and here. These are not what we're looking for, but through them we can find out the y values, corresponding y values we're looking for. So here, for example, well, we don't even need it. We know y is 0 here, but the y here can be obtained by plugging the x coordinate into this equation or this equation. Either way we get 4. So this red strip would move from 0 all the way across the shaded region, stop at 4. So it's 0 to 4. Okay, this is how we determine the limits: lower limit, upper limit. Now rest of the problem is just a simple definite integral. There are all powers. So just find the antiderivative and plug in 4, plug in 0. Alright? So copy down the 2 pi, find the antiderivative, the 5 over 1 plus 1 half, which is 3 halves. Antiderivative 1 over 5 halves plus 2 is 7 halves. Oh, wait a minute. This is 1. I'm sorry. So it's I messed up this one. It's 5 over 2 times 1 over 2 y squared. That's integral of that. Integral of this is negative 1 over 3 over 2. This is a fraction. 3 over 2 is 5 over 2. 5 over 2 y raised to 5 over 2. And this is 1 half times 1 over 3 y to the third power. So this is how we find the antiderivative power. There's a 4, we're plugging for y. There's a 0, we're plugging 5. Before we plug in those numbers, let's simplify this a little bit. They look messy. So like this term, you flip it, would be 10 over 3 y to 3 half power. This term is 5 over 4 y squared. Flip the 5 over 2, it's 2 over 5 y raised to 5 over 4 and 1 over 6 y to the third power. Alright, just a little better. Now plug in 4 for y. So we have 2 pi 10 over 3 4 to 3 half power minus 5 over 4, this is obvious, it's a 16, minus 2 over 5, 4 raised to 5 third, and 4 to the third power. Again, when we plug in 0 for y, every guy will turn to 0, so it's just 0. Anyway, with the calculator, and you can see this is volume of a solid of a revolution we're trying to determine in this problem. Alright, so again, like in the previous example, make sure you graph all these problems. We have to come up with the correct graph, right? So it's region, so you pick up a strip and revolve and so on. But in particular, with regard to this new method of a cylindrical shell, it's important you indicate the location of strip y. That's needed. Like here, that's actually the y value below. Alright, if you don't mark it, you may not be able to easily identify that. Another thing is mark the radius in the middle of the shell. Alright, so we can come up with the expressions without any confusion. Y above is 5, y below is is y. Now let me show you again. If you are not careful, if you just say draw your radius here, from the graph they look like the same. They both represent the radius, but when you try to determine the y above, y below, you can be confused. Not y above is 5, no confusing, but the y below can be a little confusing, because then you find your y below on the parabola too. Are you going to use the parabola to determine the y below? No. Alright, the correct expression is y. So similarly, if you do that the back end, then you run into the same kind of dilemma, because this point happens to be on y equal to 2x2, so it can be confusing, but you can avoid all those confusion by simply draw the radius in the middle. That's pretty simple anyway. Okay, so this is cylindrical shell method. It's yet another application of Riemann sum. So in the end, we come up with some definite integral to find the volume of revolution. Now, a lot of these problems concerning volume of a revolution, we could actually do it in different way. We could apply cylindrical shell method to do it, or we could do washer method too. In general, well, before I talk about that, you need to know both.